Imagine for a moment that you're standing on a black sand beach, maybe in Iceland. You're witnessing the result of just incredible geological violence. It's this elemental meeting of fire and ice. You have lava at, what, 1100 degrees
At
Celsius?
least, yeah. Searing hot.
Then it suddenly hits a glacier. Or just the deep, cold ocean. That reaction, that intense shock, it forges this unique material that's like a geological time capsule.
It is, absolutely. And that's what we're diving into, hyaloclastite. And, it's so much more than just cooled lava. It's this critical archive that links volcanism with the cryosphere and the hydrosphere. Our mission today is really to unpack the mechanics of this fire and water rock.
And why it's so important.
Exactly. Why its presence matters so much.
Okay, let's get into it. The name itself, hyaloclastite. That's a clue, right? It's from Greek.
It is. Hylos, meaning glass, and clast, which means fragment, glass fragment. And that's really the core concept. Hyaloclastite is formed by the rapid quenching and fragmentation of lava when it hits water or ice, or even just wet sediment. Geologists call it an volcaniclastic rock.
Autoclastic. Okay, what does that mean? It sounds forceful, but if it's shattering instantly, why isn't it considered, a typical explosive rock, like ash from a volcano?
That's a great question. The key is the mechanism. It's what we call non-explosive quench fragmentation.
So it's not gas.
No, not primarily. It's not driven by expanding gas pressure. It's driven by thermal shock. The glass cools and shrinks so fast that it shatters itself. The evidence we see in the field is amazing. We look for these jigsaw-fit textures.
Jigsaw-fit.
Yeah, you can actually see where the fragments would interlock, like pieces of a broken vase. It tells you the rock shattered right there, in situ, and didn't travel.
Oh.
It's like a snapshot of the exact moment of fragmentation.
So this is happening in some pretty dramatic places, under the ocean, at mid-ocean ridges, or even under massive glaciers.
Right, and when it erupts under ice, that's how you get those incredible flat-top mountains, tuias. You see them in Iceland and British Columbia.
Fascinating. And before we get to what happens to this rock next, let's take a quick moment for our sponsor.
This deep dive is sponsored by Embersilk. If you need help with AI training, automation, integration, or software development, or you're uncovering where AI agents could make the most impact for your business or personal life, check out embersilk.com for all your AI needs.
So if this rock starts out as just a pile of loose, porous glass fragments, how does it become solid rock? What's the transformation there?
This is where it gets really interesting. The process is called palagonitization.
Palagonitization.
Basically, that volcanic glass is unstable in water. It reacts and alters very quickly into a material called palagonite. It's a kind of a clay-rich hydrous material. And this stuff acts as a super effective natural cement.
So it just glues all the pieces together.
It does. It takes that loose debris and solidifies it into a hard rock. And it can happen, geologically speaking, surprisingly fast.
And that transformation must create this incredible variability in the rock itself.
Extreme variability, absolutely. A fresh deposit can be really soft, maybe a 1 or 2 on the Mohs hardness scale.
Super soft.
But once it's fully cemented, fully palagonitized, its compressive strength can shoot up to 180 megapascals.
I have no frame of reference for that. How strong is that?
It's strong enough to support the pressure of, say, dozens of fully loaded semi-trucks stacked on a single square meter. So you go from loose sand to something incredibly strong.
Wow. So what does this mean for applied science? How does knowing this help us?
Well, its biggest significance is as a geological recorder. It's a fantastic proxy for paleoenvironmental conditions.
A record of the past environment.
Exactly. In Iceland, for instance, you find these thick, alternating layers of hyaloclastite and regular lava flows. The hyaloclastite formed under ice.
During a glacial period.
Right. And the lava flows formed when the ice was gone, during an interglacial period. By mapping these layers, scientists can reconstruct past ice ages. They can even estimate how thick the ice was, sometimes over a kilometer thick.
And I'm guessing its economic importance comes from that soft versus hard quality you mentioned.
You got it. And things like geothermal fields or even oil and gas exploration, that variability is everything.
How so?
Well, the fresh, porous hyaloclastite can be a great reservoir rock. It lets fluids and heat move through it easily.
Yeah.
But if it's fully cemented with palagonite, it becomes impermeable.
A seal.
A perfect seal. It can trap geothermal steam or hydrocarbons underneath it. So understanding that alteration process is it's absolutely key for developing those resources sustainably. And what's really amazing is that the detailed engineering work we do on these rocks, whether it's on James Ross Island or in active geothermal zones, it helps us manage geohazards and build safer infrastructure.
Mm.
We're literally using the deep frozen history contained in these fire and water rocks to design resilient solutions for our own progress.
That's a remarkable thought. The instant shattering of rock by water preserves this ancient record of ice sheets, and that very same record helps us find future sustainable energy. It just shows how pure curiosity about a strange rock can lead directly to solving real-world challenges. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.